Every industrial operation faces an unavoidable paradox. Plant managers oversee massive asset registers filled with thousands of moving parts, but the time, money, skilled labor, and attention required to maintain them are strictly finite. Because those resources are capped, the primary challenge of industrial maintenance is rarely figuring out how to repair broken equipment. The actual challenge is deciding which equipment demands proactive intervention and which can be safely left alone. Historically, operations have navigated this problem by relying on the subjective experience of their teams. Maintenance prioritization was often decided by gut feeling, institutional memory, or simply the loudest voice in the room. Relying on subjective experience guarantees a misallocation of the maintenance budget. Skilled labor ends up spread dangerously thin across the facility, reacting to whatever issue feels urgent that day. Managing physical assets without a rigorous mathematical framework turns industrial maintenance into a reactive gamble. To treat maintenance as a strategic business investment, an operation must replace opinions with evidence. When plants operate without an objective criticality framework, they consistently suffer from two expensive failure patterns at the exact same time. The first is the over-maintenance of low-consequence assets. This looks like a maintenance department deploying expensive vibration sensors, running full reliability analyses, and hoarding critical spare parts for basic lighting circuits or general service pumps. These assets consume budget, yet their failure has zero impact on actual production. While money is drained on trivial assets, the second failure pattern takes hold: the dangerous underprotection of genuinely critical equipment. An operation might run a massive primary crusher using only basic scheduled checks and OEM recommendations. By applying the same baseline maintenance tactics to everything, the engineering team ignores advanced predictive monitoring on the machines that actually drive revenue. Underprotecting the production bottleneck directly invites catastrophic failures. The result is extended unplanned downtime, severe safety incidents, and massive repair costs. ISO 55001 Aligned Asset Criticality addresses this by establishing a systematic, risk-based equation to define the priority of every asset in the register. Establishing a strict mathematical framework to align maintenance investment with actual business risk is the only sustainable way to protect the workforce and the bottom line. The foundation of this framework rests on a specific definition of risk. Risk is the mathematical product of two intersecting variables: the severity of a hazard and the likelihood of its occurrence. This matrix maps out the equation across a two-dimensional plane. The x-axis represents the consequence impact of a failure, and the y-axis represents the likelihood of that failure occurring. Older models often evaluated consequence alone, forcing any potential safety hazard to be flagged as top priority. If an event is treated as critical, regardless of rarity, the focus of the maintenance team is immediately diluted across too many assets. To prevent that dilution, the likelihood axis cannot be based on theoretical worst-case scenarios. It must be strictly derived from historical failure data, logged accurately in the organization's computerized maintenance management system. By demanding hard evidence across both axes, the operation creates a targeted, actionable strategy. Assets are only prioritized when severe consequences overlap with a credible likelihood of occurrence. To calculate the x-axis, the consequence impact score is generated by weighing four distinct business parameters. First, the production impact. Second, safety and environmental harm. Third, the direct cost of repair. And finally, legal or reputational exposure. This chart illustrates the crucial mathematical engine behind that scoring: a geometric rating scale. Instead of counting 1 through 5, consequence levels are scored as 1, 3, 9, 27, and 81. A standard linear scale of 1 to 5 averages out extremes. If a severe production loss is averaged with a relatively cheap replacement part, the math produces a flat, moderate score. The geometric sequence intentionally breaks that averaging effect. A catastrophic level 5 score of 81 permanently skews the weighted average upward, regardless of the other parameters. This directly translates to the real world. A scenario involving a potential fatality or a massive environmental spill cannot be mathematically masked just because the physical repair cost of the broken valve is $50. Without this exponential scaling, existential business risks can easily hide in the middle of a maintenance spreadsheet, appearing as a manageable priority. The geometric scale is a deliberate mechanism. It forces catastrophic risks to the surface, presenting them clearly so leadership is compelled to manage them. Effective assessment requires a shift in perspective. Assets cannot be evaluated as monolithic objects. Take a 100-ton haul truck. Asking a team, how critical is this truck, produces useless subjective answers. Instead, the framework demands that engineers evaluate specific failure mode scenarios within the truck's individual subassemblies. Look at this matrix. We can plot our first scenario, an engine overheating. Historical data shows this happens frequently, giving it a likelihood of 3, but the impact is a manageable delay, scoring a consequence of 27. Now we plot the second scenario for the same truck, a brake failure on a steep haul ramp. The CMMS shows this is where, a likelihood of 2, but the geometric score for a runaway truck is a catastrophic consequence of 81. The discrepancy in risk between these two dots is vast. The brake failure sits much further out on the risk plane, representing a significantly higher threat to the operation. This introduces the worst-case rule. The single highest risk failure mode scenario explicitly dictates the overall criticality class, A, B, or C, for the entire asset. The truck is classified based on the brake failure, not the engine heat. Generating precise data points like these requires a cross-functional governance team. Engineering, safety, finance, and operations personnel must debate and validate the scores together to eliminate individual bias. The worst-case rule ensures an asset is rigidly protected against its single most dangerous vulnerability, regardless of how many minor, low-risk issues it experiences daily. A mathematically perfect criticality matrix that lives in a desktop spreadsheet delivers zero value to the plant floor. To be effective, the output of the matrix must be hard-coded directly into the organization's enterprise system. In a platform like SAP, the result is loaded into the ABC indicator field on the equipment master record. Once populated, this specific field acts as the master filter for the entire maintenance operation. It immediately begins driving automated work order priorities, scheduling dashboards, and compliance reporting. This configuration step removes human hesitation. It transforms a theoretical workshop discussion into an auditable, system-enforced standard that planners rely on every day. Deep system integration converts the mathematics of risk into strict, automated operational governance. This flowchart illustrates the decision cascade. The single ABC indicator splits the entire asset register into distinct, carefully managed maintenance ecosystems. Following the Class A stream reveals strict requirements. Critical assets mandate formal reliability-centered maintenance analyses, continuous condition monitoring, and immediate escalation for all breakdown work orders. The supply chain is tightly controlled here as well. Critical spare parts for Class A equipment must be physically held in the warehouse at all times to prevent extended downtime. Moving across to the Class C and low streams shows a drastic reduction in tactical requirements. For low-consequence items, standard OEM schedules are completely sufficient. In many cases, a deliberate run-to-failure strategy is entirely valid. The matrix mathematically proves to leadership that the organization should be spending less time and money on these lower streams. Explicitly categorizing low-impact equipment provides the engineering team with organizational permission to stop over-maintaining. This instantly frees up budget and skilled labor that was previously wasted. Asset criticality provides the authoritative permission to reduce maintenance on the trivial majority, precisely so the operation can fund the protection of the vital few. This chart visualizes the ultimate result of the framework. A mature criticality program naturally aligns with the Pareto principle. It successfully isolates the 20% of assets that account for 80% of the operational risk, ensuring they command the vast majority of the maintenance focus. By structuring risk objectively, finite resources are no longer a liability. Asset criticality aligns maintenance effort with business risk, replacing a reactive culture with a targeted investment strategy.